Hello everyone, this is Doug, and in this video I'm going to introduce you to the concept of chemical equilibria. Right, so chemical equilibrium is just basically it's a dynamic equilibrium in which it appears the concentrations of reactants and products are no longer changing, and that's because the rate of the forward reaction and the back reaction are the same. Right, so one thing I want to highlight here is that this is a dynamic equilibrium, and that just means that things are constantly changing. A static equilibrium would be like, you've imagined like a teeter-totter with two equally sized kids on it, or like a balance, a scale where you have equal weights on it, right? That would be an equilibrium, but it's static, nothing changes. Dynamic means that things are still changing, and I'll show you more what that means in a second. And in chemical equilibria, right, the idea is that people always think that it's the amount of stuff, reactants and products are equal because it says equilibrium. But what's equal is the rates of the forward reaction and the back reaction. That's what's equal. And so what we need to talk about here is if you look at any given reaction, right, say I have a reaction that looks like this, right, how am I going to be able to tell if there's a chemical equilibrium or not? And if there is, which side of the equation are we talking about? We're talking about the product side or the reactant side. And the way that we're going to determine that is by looking at this change in energy, right? It's all about what this delta E is. Now, for some of you, right, this delta E might be represented in terms of Gibbs free energy. So Gibbs, so if you're watching this, you're not in my class, Gibbs free energy, right, is talking about is it exergonic or endergonic, and that's dependent on the enthalpy and entropy changes. For my class, or if you're watching this and you're like an introductory level student or 100 level student or non-major student, this delta E is usually given as straight up just enthalpy. Because often in lower level classes we just kind of ignore entropy because it's very strange and just talk about enthalpy. So whatever your change in energy is, whether it's Gibbs or enthalpy, that's what we're talking about, the difference in energy there. And again, for my students, enthalpy is going to be what we really look at. So let me show you this simulator so you can kind of visualize kind of what we're talking about. All right, folks, so let's look at the first example here, right? So let's look at something that is very exothermic, or very, very downhill. And so this is sort of like my energy diagram, right? So I have the A's over here, the B's over there. I've got my reversible reaction. And just the question I want to ask myself is what's going to happen when I add a bunch, let's just say 100, let's say 50 A's, and I start this reaction, right? What's going to happen over time here? Right, so I want to know what's going to happen over time. I'm going to cool this down so we can see things. But probably as you're seeing, right, those A's turn into B's really quickly. And I'm not going to sit here forever because I think you'll probably get the point. But if I sit here and I keep letting the reaction occur, what's going to happen, right? Am I going to have A's turning into B's and B's turning into A's? Or is this pretty much just going to go one way? It's pretty much just all the A's going to turn into B's. And hopefully you can bear with me here, right? We're going to see, this little guy over here on the far left is probably not going to make it by the time you watch it, but basically, this reaction's pretty much just going one way. It's just going to the right. And that's because it's such a downhill reaction that we're going to see everything basically just turn into B's because it's so much more stable and so much more favorable. All right, so this reaction, we don't really have a chemical equilibrium set up. We don't have things going back and forth. This is just a one-way type of reaction. Right, and so in that equation, let me just redraw that energy diagram. That was a very exothermic, right? This was a very, very exothermic reaction. Right, if you looked at this, your delta H here, your difference in energy was very negative and very large. It was negative and it was very large. And so when we have a very large, so when we have a very large, very negative, very exothermic reaction, we don't even bother with the equilibrium arrows. We just said that A turns into B, that this is just a one-way reaction. One-way reaction. Or sometimes we might say things like that it goes to 100% completion. Right, that basically all the A's are going to turn into B's because the B's are so much more stable. Right, the B's are very, very, very stable. And that apparently the A's are very unstable. And so, of course, if you start off very unstable, everything's going to want to become more stable. And so you release a lot of energy and you get a one-way reaction. But of course, this isn't all reactions, right? So let's take another look at that simulator. So now let's consider a different version, right? So let's stop this and let's clear this all out here. What if I have the other way, right? So what if I have one that is very uphill, has a very positive delta H value, a very positive delta E value, really uphill. Again, I'm going to put 50 things in A. I'm going to start this. And as you probably can guess, right, if it's a really big hill, if it requires a lot of energy, we don't really see anything happen, right? I'm not making any B's at all. This would just not be any sort of reaction. I'm not making any B's at all. There's no equilibrium set up here because the difference in energies is just too big. That delta H value is just too big. And so it doesn't really matter how long we sit here, I'm not going to form any B's. I don't see anything happen. Right, so in this case, we had kind of the opposite, right? We went up, we had a very endothermic reaction. Very endothermic, right? If I took a look at the change in energy here, right, my delta H would be positive and it would be large. Right, so I have a very large positive delta H. I got to put a lot of energy in, right? It requires a lot of energy. In this case, when we're talking about A going into B, sometimes you'll see just a big old X. Just a big old X here, showing that there's basically going to be no reaction. Because it just requires too much energy to go up the hill, right? Because you start with something stable, and you're trying to turn it into something unstable. And that requires a lot of energy. You got to do a bunch of fancy things to try to get reactions to do that. Change reagents or add a whole bunch of temperature and take advantage of Le Chatelier's principle, which we'll talk about in future videos. But if you have a really high hill to climb, if you're very endothermic, it requires a lot of energy. Oftentimes we just see that there's an arrow with an X in it, or we just flat out write that there's no reaction, right? So it's the opposite of having a 100% reaction. This is like having a 0% reaction. And so neither of these are chemical equilibria. Let's look at an example where you might actually have a chemical equilibrium, where we can establish an equilibrium. But so now let's look at a more subtle example here, right? So let's say we have an example like this, where I have a much smaller difference in the energy levels between my starting materials and my products, right? And so for this one, I'm going to put 100 A's in. I'm going to lower these actually just a little bit. If I start this now, right? So I'm going to have 100 A's that I've added. The question is, where do I expect for these to end up? Are they all going to go to the B side, or are none of them going to go to the B side? Since the B side is lower in energy, right, we expect things to go over there because they're more stable, right? That those molecules are going to be more stable if they turn into B because it's lower in energy. And so we'll go ahead and we'll let this run. I'll add some heat so we can get to equilibrium a little bit faster here. But as you can see, right, this is a very different example than those first two, right? It's not like I have a one-way reaction where all the A's turn into B's, essentially. It's not no reaction where I had no A's turn into B's. In this case, I have A's turning into B's, I have B's turning into A's. You could watch any one of these spheres going back and forth, and you can see that there's changing a lot. But what you will notice if you look over here at the number of molecules in the chamber in the upper right-hand part, it looks like the number of A's is about 45-ish, 40, maybe 40-ish. You know, it's flipping around, somewhere in the 40s. And then the B's are between 55 and 60 the whole time, right? So they've kind of leveled out to about approximate ratio. Let's just say this is 40-60. And it's just going to stay that way. It's just going to stay that way, right? It's not going to like all of a sudden the A's are going to drop to 20 or the A's are going to go up to 90. It's going to be about this 40-60-ish ratio if you look at this average over time. Now, what's cool here is that it doesn't really matter, right? So here's my approximately 40-60. Now, if I add a whole bunch more stuff, right? So let's say I add 162 instead of 60, so I'm adding 100 things. I still expect a roughly 40-60 ratio. So if I added another 100 instead of 40-60, now I'm expecting 80-120. That's what I should expect to get, because these ratios are set up, these equilibrium ratios are set up a certain way for every single reaction that they're always going to try to get back to that ratio. So let's see if we get back to that roughly 2 to 3 ratio, or roughly in our case, we're said about 60 to 120-ish on average. Whoops, let me not blow up my simulator. And sure enough, we've given it a few seconds. These are going really fast. But you can see, right, that this is in the 60s. So now it's in 70s, 60s. But it's about 60 to 120 still, maybe 70 to 110. Let me slow this down a little bit so you can see these numbers better. Right, it's still about that ratio. It looks like it's more 70 to 130-ish or so. Numbers are bouncing around. But the idea is that it goes back to that ratio. This would be an example, though, of a chemical equilibrium. Right, it looks like roughly there's the same amount of A's as there have been. Right, there's looks like about 80, about 70 or 80. And then roughly about the same amount of B's here, namely about 120-ish, bouncing around 120. So it appears that the reaction has stopped, even though clearly, if you look at this, there's lots going on, right? This is what I mean by a dynamic equilibrium, right? Things are still moving all the time, moving left and right, left and right. A's are turning into B's, B's are turning into A's. But it's an equilibrium because the rate at which A turns into B and B turns into A is the same. So overall, that number doesn't really change that much on the upper right-hand side, right? That 70, 80-ish A's and that 120-ish B's aren't really changing all that much. And the same thing would happen, right, if I pause this, I'll reset all of these. Same thing would happen if I had a small difference, but it was uphill, if it was endothermic instead. Same thing. So I'll put 500 A's in this case. Right, so we'll put 500 A's, I'll add a little bit of heat so we can get to equilibrium faster. And we'll see, right, already definitely we saw some B's forming, but we'll see again that this should end up at some sort of basically a constant number for A and a constant number for B once it reaches equilibrium. So while we still see net changes in A's and B's, it hasn't reached equilibrium. Once we no longer see a net change between A's and B's, then it has reached equilibrium. And so I'm going to let this go a little bit longer, see where we kind of settle down. Probably, it looks like it's reached about equilibrium because it looks like I have roughly, what was that, 280, 290 to about 210-ish in terms of numbers. And we could sit here all day, and the number's not going to change from that. It's going to be about 280 to 210-ish, no matter what, because it's reached equilibrium. And again, it's a dynamic equilibrium. So what we're looking for here, right, to have a chemical equilibrium is that we need a small difference in those energy levels. It doesn't matter if it's small and endothermic or small and exothermic. That'll just depend on what you're favoring. Are you favoring products or reactants? But the idea is that if there's a small difference, then you're going to have both A's and B's, and they're going to be interconverting. If there's a gigantic difference, that's when we saw there was no reaction or there's a 100% reaction, and we represent that using those different arrows. So in this example, right, we had different examples, right? We had a smaller change in energy, a smaller difference in energy here, right? And like I said in the video, it doesn't matter if you're going uphill or downhill. What matters is that that difference in energy is small, right? So now if you take a look at your delta H, the idea is that this needs to be small. In this particular case, it's negative, but it could be positive. It doesn't matter if you're going uphill a little bit or downhill a little bit, you can still have a chemical equilibrium. So, but it could be positive. Doesn't matter. What matters is that it's a small difference. And so in this case right now, if we're talking about reactants turning into products, now we do have an equilibrium. We can establish an equilibrium where A's are turning into B's and B's are turning into A's. And so we use the equilibrium arrows. Right, so these are equilibrium arrows, where they're showing that you have the forward reaction occurring and the back reaction occurring. And remember that the idea here is that those rates are equal. The rate of the forward reaction and back reaction are equal. So the rates are equal. And that's why it's called an equilibrium. It's because it's the rates that are equal, not the amounts of stuff, right? Remember in those videos, the number of A's and B's weren't equal. They were just kind of constant. They seemed to remain constant because A's were turning into B's at the same rate that B's were turning into A's, is the idea. So this would be an example of a chemical equilibrium, right? We need to have a small change in energy, whether you're talking about enthalpy or Gibbs, and that establishes the rates that are going forwards and backwards. That establishes that they're the same. Now, to kind of sum up, right, the idea is, right, again, is chemical equilibrium is a dynamic equilibrium like we saw in those videos, right? Lots was happening, lots was still occurring. It wasn't that it just stopped, it's that lots occurs, it's just that the rates of the forward reaction and the back reaction are the same. That's what's equal. Every reaction has its own equilibrium. There's no way you can just look at a reaction and be like, oh, I think the equilibrium value is going to be 5, or I believe it's going to be 0.00012 or something like that. You have to establish it experimentally. So no one's going to ask you to just say what it is. You might be able to guess if it's large or small based on other things, but you have to calculate it experimentally. So, importantly, some common misconceptions here. What I often hear students, so these are all false, right? These are all false. When a reaction establishes equilibrium, molecules are no longer reacting or changing. That is false, right? They are changing. The A's are still turning into B's, B's are still turning into A's, right? Your forward reaction is still occurring, your back reaction is still occurring. So it's not true that they're no longer reacting. They are still reacting. It's just that it appears to us on a macroscopic scale because the total amount of stuff doesn't change to us. But even though the molecules are still moving around like crazy and interconverting like crazy. Another thing that I hear students say all the time that is false is that when a reaction reaches equilibrium, the amount of reactants and products are equal. Also false, right? It does not have to be equal. People hear equilibrium and they think, okay, the amount of products and reactants are equal. That is not true. It could be true for some reaction, but again, you'd have to look at the K value. You'd have to know that the K value, for example, equaled 1. To be able to predict if the amounts of products or reactants are equal. They're almost never going to be. If you're either going uphill or downhill, they're not going to be. If you're going downhill, you expect more products than reactants. If you're going uphill, you expect more reactants than products. So it's not that the amounts of them are equal. That is false. And the last thing that I hear all the time is that people feel like they can figure out how many more products or reactants there are by looking at a balanced equation, right? So if you balance this equation here where you have 2 ethanols, you make 1 diethyl ether, and you make water, that for some reason there should be twice as much of this as that because there's a 2-to-1 ratio, so that you'd expect more of this at equilibrium than that at equilibrium, right? So that students will often say, oh, at equilibrium, so I'll put at equilibrium. So at equilibrium, people want to say that they're... Sorry, this is just all... let me just rewrite this. I was being lazy. People think that at equilibrium, that this means that there should be twice as much of this, twice as much of that as everything else because there is a 2-to-1 ratio. That is not true. You're just balancing an equation. You're just saying what the recipe is. That has nothing to do with the final concentrations in the end. What has to do with the final concentrations is, are you exothermic? Are you endothermic? If you go downhill, you have more products. If you go uphill, you have more reactants. That's what you see. So all 3 of these are false. None of these are true. So that's our introduction to chemical equilibrium. Again, I haven't talked at all about what this K is, so don't worry about what the K value is, but there are values that tell you exactly what those numbers, what those ratios should be. That'll be for a future video, but most of my students don't need to know that at this point. But that's what a chemical equilibrium is, right? We have a small difference in the beginning and ending energies, and lots of reactions are still occurring at the same time. They're just occurring at the same rates. So if you have any questions or comments, please leave them down below. And in the next video, I want to talk about Le Chatelier's principle, which is just predicting what will happen when you mess with a equilibrium, when you perturb it, when you disturb an equilibrium. How is it going to react to that? So keep an eye out for that video. Take care.